Hi everyone, in this video we're going to look at how to do Lagrangian mechanics when you have constraints on your coordinates. So what I mean by that is maybe your particle is constrained to move on the surface of a particular sphere, or maybe it's a bead moving along a wire of a particular shape, but some kind of scenario in which not all possible displacements are allowed. Your particle can only move in certain ways. So we're going to start from Hamilton's principle of stationary action. We're going to derive the Euler-Lagrange equations, then we're going to incorporate the constraints and see how they modify the Euler-Lagrange equations, and then at the very end we are going to do some physical interpretation of the results and try and get some intuition as to what the equations of motion actually mean. So let's start with the definition of action. The action is the S quantity that I've defined on the screen here. It's the integral from t1 to t2, in other words, just over the period of time that you're interested in, of this quantity L, which is the Lagrangian. I'll write down here that Lagrangian is defined as T minus V, where T is kinetic energy and V is potential energy. And it's a function of three things. Q, which are generalized coordinates. Generalized coordinates meaning it could be ordinary Cartesian coordinates, it could be like spherical polar coordinates, or something more complicated, just a set of values which defines the state of your system at a particular time. So Lagrangian depends on generalized coordinates Q. It depends on their derivatives, which I've written as Q dot, and it also could depend explicitly on time. I've written Q and Q dot as vectors, and just to make it explicitly clear, I'm going to write out that your Q vector, vector of generalized coordinates, is just a collection of individual, generalized coordinates. So you could write it out as Q1, Q2, and so on, all the way up to Qn, in the case where you have n coordinates that describe the state of your system. So this delta S equals 0, that is Hamilton's principle, which basically says if you were to make some small variation in the path through configuration space that your system takes, then that would not make any difference to the action, right? That's what we mean by the action is stationary. So to explore the consequences of that, we're going to imagine taking your coordinates Q, generalized coordinates Q, which are a function of time, you're going to make a modification to them. So you're going to take the Q's and turn them into Q plus delta Q, where delta Q is a little adjustment, a small change in how your coordinates are behaving over time. So if we do that, we want to ultimately know what resulting change would you get to your action, because we want to set that equal to 0. So if we take Q to Q plus delta Q, firstly let's consider the effect that would have on the Lagrangian. So we're going to write the resulting change in the Lagrangian as delta L. Well, to first order, assuming delta Q is small, that's an assumption we're going to make, then we're going to get a partial derivative with respect to Q, so dl by dq dotted with your delta Q vector there. If it looks strange to differentiate by a vector, I'm going to clarify what I mean by that in a second. But also note that when you change your Q's, you inevitably also change their time derivatives. And so I'm going to have to add on a contribution, which is dl by dq dot dotted with delta q dot. So what does this differentiation by a vector notation mean? Well, it's just a shorthand for the expanded version, which is dl by dq1 times the change in q1, delta q1, plus dl by dq2 times delta q2, and so on, all added together up until dl by tqn times delta qn. Right, so it's just a much more concise way, writing it as a dot product, much more concise way than having to write out all the terms, or indeed even write it out as a sum. I'll also mention at this stage that the one restriction we're going to impose on these delta q's, and let me write this down, the one restriction on the delta q's is that delta q evaluated at a time of t1 and delta q evaluated at a time of t2, those both have to be 0. And physically what that's saying is we are investigating the motion between a fixed given start point and a fixed end point, right? So in other words, there can be no change to our perturbed paths at the beginning and end points. That's why those deltas are 0. So anyway, that delta L that we've got is in turn going to lead to a delta S, a change in the action. And the change in the action is just going to be the integral from t1 to t2 of the change in the Lagrangian, which we already know is dl by dq dot delta q plus dl by dq dot dotted with delta q dot, and then that's integrated with respect to time. So now let's focus on this delta q dot bit, because that means the change in the time derivative of q. Now that means take the new time derivative of q after you've made this small adjustment to the path that the particle is taking. Take the new q dot, subtract off the original q dot. But because differentiation is a linear operation, it doesn't matter whether we differentiate first and then subtract the two values, or whether we subtract the old q's from the new q's first and then we differentiate. And so the delta q dot can equivalently be written as the time derivative d by dt of delta q. So we basically swapped the order of the delta and the time derivative. Now the reason that's useful is we can then do integration by parts on the second term of our integrand, because the second term is now of the form some term dl by dq dot multiplied by a derivative d by dt of delta q. That's exactly the kind of thing that we can do integration by parts on. So if we integrate the second term by parts, we've got the integral from t1 to t2. First term is going to stay the same, right? That's still dl by dq dotted with delta q. The second term, we're going to get a minus sign as we do when we integrate by parts. We put the time derivative d by dt onto the dl by dq dot. So we've got dl by dq dot, and then we remove the time derivative from the second bit, and so now we've just got that dotted with delta q, and that is a time integral. And when we integrate by parts, we also get these boundary terms, which are going to be, remember, this is the bit that we integrated by parts. The boundary term associated with that will be dl by dq dot dotted with delta q. We've got to evaluate that at t1 and t2 and subtract those. But then at this point, remember that we had this restriction on our delta q's, that they're 0 at t1 and t2. In other words, the start and end point of our trajectory through configuration space is fixed. And so this delta q part is 0, both at t1 and t2. And so we can just ignore that second bit because it's equal to 0. So if we just tidy things up a bit and do a little bit of factorizing, our current form of the delta s is the integral from t1 to t2 of dl by dq. I'm going to factor out the delta q. So dl by dq minus time derivative d by dt of dl by dq dot. That whole thing dotted with delta q and integrated with respect to time. Now remember that Hamilton's principle said that delta s should be 0, so we can set that integral to 0. But now remember that we haven't said anything in particular about this delta q, right? That could be any allowed displacement. It's not some fixed quantity. It could be any generalized displacement which is consistent with any constraints on the system. But the only way that we can make this integral 0 for any allowed set of delta q's is by making the integrand itself 0, right? So the entire integrand should be 0. And so if I just write out some of the terms of that, in terms of the individual coordinates, you're going to get dl by dq1 minus d by dt of dl by dq1 dot. That multiplied by delta q1. And then you're going to get all of your terms in the middle, and if you go straight to the final term, you're going to have dl by basically the same thing, but with the 1 replaced by n, because that's the final term. So dl by dqn minus d by dt of dl by dqn dot times delta qn. Now, if we were only thinking about unconstrained motion, then we would be able to say that, remember, this is supposed to be 0. If there are no constraints, then we'd be able to say that because the delta q's are all completely independent of each other, the only way we can make this equation work is that we would have to set the coefficient of each delta q individually to 0, right? Because the delta q's would be totally arbitrary, and no matter how much delta q1 you added onto delta q2, for example, you could never make that equal to 0 unless the coefficients of the delta q's were individually 0. So, for example, this bracketed term there would be 0, this bracketed term here would be 0, and then we've derived the Euler-Lagrange equations, right? It says that for any particular coordinate qi, dl by dqi minus d by dt of dl by dq dot I is equal to 0. But what about if there are constraints? Well, in that case, the delta q's are no longer independent of each other, right? For example, maybe you can't change q1 without changing q2, and that means because the delta q's are no longer independent, you can't set the individual coefficients to 0 anymore. So we've got to think a bit more carefully about how to deal with constraints. So let's think about how to actually mathematically represent a constraint. So I'm going to say we're going to set the q's to be constrained. So the q's are constrained in such a way that some function f of the coordinates and possibly time is equal to 0. Mathematically, this type of constraint that can be expressed in this form is called a holonomic constraint. We're going to focus on this type of constraint. Note that it doesn't involve the generalized velocities, but basically it's just some equation that links together the coordinates. Let's think about a couple of examples of where this might apply. So let's say you have a 2D system where your generalized coordinates are just Cartesian x and y, but maybe your system is constrained so that your particle can only move in the horizontal direction. So if you can only move in the horizontal direction, then your y coordinate is a constant, and you could write that as, let's say, y minus y0 equals 0, where y0 is just a constant number. Or to give you a slightly more complicated example, where your coordinates are mixed together, I'm going to write down the equation r minus a theta is equal to 0, where here our generalized coordinates are r and theta, which are polar coordinates, and a is a constant. What this would do is force your, let's say it's a particle moving around, it would force your particle to be moving on like a piece of wire in the shape of an Archimedean spiral, which has the equation r equals a theta. So these are just a couple of examples of constraints that you could cast into this holonomic form. So if f always has to be 0, that restricts the possible changes that we're allowed to make in our coordinates, in other words, the delta q's, right? So this equation has to be satisfied. What does that imply about the changes that we're allowed to make in the coordinates? Well, if you think about what delta f would be, if you change q by a particular amount, it would just be the partial derivative of f with respect to q dotted with delta q, and then again, if we just expand out some of those terms to get an idea of what that actually means, it's df by dq1 times delta q1 plus a whole bunch of terms all the way up to qn, so df by dqn times delta qn. And because your function has a constant value which happens to be 0, any change in that function also has to be 0, right? So we now have this additional constraint which restricts the possible delta q's that we're allowed to make. So at this point, I'm going to do something that might look a little bit mysterious, but I'm going to explain why I'm doing this afterwards. I'm going to label this first equation 1, label this second equation 2. I'm going to take equation 1 and add on some multiple, which I'm going to call lambda, of equation 2. Note that lambda doesn't necessarily have to be a constant. It could be a function that depends on the coordinates or depends on time. I'm just going to write it as lambda. It's the factor by which we're scaling up equation 2. So the reason for doing this is that your resulting equation can still be grouped into these sort of factorized terms in terms of each individual delta q. For example, the first term is going to be dl by dq1 minus d by dt of dl by dq1 dot. This time we're going to add on from this term over here, our df by dq1 term, we're going to get an additional factor of lambda times df by dq1, and then that whole thing multiplied by dq1. Then you get all your other terms all the way up to the qn term, and because the right-hand sides of equations 1 and 2 are both 0, the right-hand side of a resulting equation, when we add them together, is still going to be 0. Now notice that by introducing this new factor of lambda, we've introduced an extra degree of freedom in our equation, right? Previously, before we introduced the constraint equation, we had n degrees of freedom. Each q could vary independently from the others. By introducing our constraint equation, we reduced the number of degrees of freedom by 1, which is why you could no longer set those individual coefficients to 0. But now I've introduced this extra factor lambda, and so we've again got n independent degrees of freedom. And so because we can choose lambda to be whatever we like, we can choose lambda in such a way that we do in fact make all of these individual coefficients of all of the delta q's 0, even though the delta q's are no longer independent of each other, right? Because we can choose lambda however we want to. And so if we were to write out the resulting equation for some arbitrary coordinate qi, you would end up with dl by dqi minus d by dt of dl by dqi dot plus this as yet undetermined factor lambda, which by the way is called a Lagrange multiplier, multiplied by df by dqi. That should be equal to 0. Now, as yet, we don't know what lambda actually is. Because I can vary from 1 to n, this is really a set of n equations, but we have n plus 1 unknowns, right? We have all of the coordinates qi, and we have lambda as well. But remember, we do have an extra equation constraining our system, which is this f of q and t is equal to 0. So if we take the set of differential equations and our holonomic constraint together, we have n plus 1 equations, right? N from the differential equations, 1 extra from the constraint. But we also have n plus 1 unknowns, which are the qi's and the lambda, which is perfect. So we actually do have enough information to solve for everything. In fact, if we hadn't introduced that lambda, the system would be mathematically over-constrained in the sense that you would have n plus 1 equations, right? You've got your n differential equations plus the constraint, but if we hadn't introduced the factor of lambda, we would have had only n unknowns, and so that would basically just be impossible to solve in a consistent way. Now for this video, for simplicity, I'm going to keep things to just one constraint, but you can extend this very easily to as many constraints as you like. For example, if you had another function g of q and t, which was supposed to be equal to 0, then you would just add on another Lagrange multiplier. So like in your equation here, in addition to this lambda df by dqi, you would get like a plus mu dg by dqi and so on. And you just add one Lagrange multiplier term for each additional constraint. So that's a straightforward extension, but I'm going to, for the rest of this video, just focus on the case of a single constraint. Now we've got our equations of motion. We can solve these and find out how our system evolves with time. But let's just take a moment to interpret these various terms, in particular, focusing on what the meaning of that mysterious factor lambda actually is. First thing I want to do is look at this dl by dq dot term. So let's imagine for the moment that we're in Cartesian coordinates. So our qi's are just x, y, and z. Then your dl by dqi, what would that actually be? Well, remember that L is the kinetic energy minus the potential energy. Potential energy only depends on position, so the q dot dependence of L must be coming from the kinetic energy part. So dl by dq dot I is the same as dt by dq dot I. And assuming that we're working in Cartesian coordinates, that's the same as d by dq dot I of a half times the mass of the particle times q dot I squared, right? It's just half times mass times velocity squared. And then you just differentiate that with respect to q dot, and you get the mass times qi dot, which in Cartesian coordinates is just the momentum in direction I, right? In other words, in the x momentum or the y momentum or the z momentum, but we're just going to denote that as pi. Now, by analogy with the Cartesian case, more generally, we call this the canonical momentum. You can think of it as like a generalized momentum. It's not always just mass times velocity. In particular, if you've got an angular coordinate, it can be angular momentum, but we define it by analogy with this Cartesian case. So what do your equations of motion then say in terms of the canonical momentum? Well, if we take this term, the minus term, over to the other side, then we end up with the fact that dpi by dt, which is just that middle term, right, has to be dl by dqi plus that lambda term, lambda df by dqi. So the left-hand side is the rate of change of the canonical momentum. So already we can start making an analogy with Newton's second law, which says that the resultant force on an object is the rate of change of its momentum. So that already looks a little bit like a generalized version of Newton's second law. We can take the analogy a little bit further by noting that dl by dqi well, the position dependence of L must come from this potential part, the minus V part, because kinetic energy doesn't depend on position. So dl by dqi is minus dv by dqi, which is basically the, well, it's the derivative of the potential in the I direction, which again, if your q's are Cartesian coordinates, that's the gradient of the potential in a particular direction, which is the force. More generally, regardless of what the QIs actually are, whether they're angular or linear coordinates or something more complicated, we can interpret that dl by dqi term as like a generalized force coming from the potential. So we've got rate of change of canonical momentum is the generalized force from the potential, meaning that this lambda df by dqi term could also be interpreted as some kind of generalized force. And because that's a generalized force associated with the constraint F equals 0, that is the generalized force which is keeping the constraint satisfied, right? So I'm just going to note down that this is your, basically your constraint force, and the interpretation of what that means will vary depending on the system. But for example, if it's a bead on a wire, then it will be the normal reaction force that keeps the bead moving perfectly along the wire, right? It'll be the contact force between the bead and the wire itself. We can actually also come up with a nice geometrical interpretation of that final term. And in particular, we can justify why it is proportional to the derivative of f. So to do that, imagine your system moving through configuration space, so the space of all the generalized coordinates. And remember that it can only move along basically this surface defined by f equals 0. So let's represent that surface as just some kind of curve like that. So let's say you have your particle sitting at the bottom. Maybe this is a wire, so it's a bead moving along a wire. Maybe at one instant, it's moving in that particular direction. Okay. If there were no constraint force, then it would just keep going in the direction that it wants to go in. The constraint force basically pulls it back onto the allowed surface, right? So remember that this is the surface of f equals 0 in configuration space. The constraint force will pull it back to the surface in the most direct way possible. So the easiest way for it to do that is to sort of pull back in a way that's perpendicular to the surface itself. Now, if you're familiar with vector calculus, you'll know that the vector which is perpendicular to a surface over which some function takes a constant value is proportional to the gradient of that function. So the direction of this constraint force arrow that we've drawn on should be, well, it should be proportional to the gradient of f. And we can call that constant of proportionality lambda, which matches up very nicely with this lambda df by dqi that we got using more formal mathematical methods, because the gradient is just the vector of all of the derivatives in qi space. So that's how you can deal with constraints in the Lagrangian formalism. This has all been a little bit abstract, so I am planning to do a video in the near future where I go through a specific example of this in practice to see how we can actually use it. So I hope to see you again soon for that example.